In machine learning, building a model isn't just about getting high accuracy on training data. It's about finding the right balance, a balance between learning too little and learning too much. In this video, we will break down one of the most important ideas in machine learning. At its core, machine learning is about generalization. We train models on historical data so they can recognize patterns, understand relationships, and make accurate predictions on new, unseen data. The goal is not memorization, the goal is learning patterns that transfer beyond the training set. Let's start with underfitting. An underfitted model is too simple to capture the real structure of the data. It's like trying to draw a curved road using a straight ruler. Important patterns are completely missed. You will typically see high training error and high validation error because the model just doesn't have enough capacity to learn. This is known as high bias. The model makes overly simplistic assumptions about reality. In contrast, this plot shows underfitting. The blue dots again represent noisy data and an underlying exponential trend. But the orange line is a very simple model, essentially a straight line. Because the model is too simple, it completely misses the exponential growth pattern. As a result, both training and validation errors remain high. This is known as high bias, where the model's assumptions are too restrictive to capture reality. On the opposite extreme, we have overfitting. Here, the model fits the training data almost perfectly, including noise and outliers. But when it sees new data, performance drops sharply. This happens because the model is too sensitive to small changes in the training data. That sensitivity is called high variance. It's like memorizing answers for tests instead of understanding the concept behind them. In the plot, the blue dots represent noisy training data, and the orange line shows a highly flexible model. Notice how the curve bends sharply to follow almost every data point, including random noises. While this looks impressive on training data, it's actually a problem. The model is reacting too strongly to small fluctuations, which means it will struggle to generalize to new data. This behavior is a classic example of high variance, where the model memorizes instead of learning. This brings us to bias variance trade-off. On one end, high bias leads to underfitting. On the other end, high variance leads to overfitting. The ideal model sits right in the middle, complex enough to capture real patterns, but simple enough to ignore random noise. Finding this balance is one of the central challenges in machine learning. Bias measures error caused by incorrect assumptions. High bias means the model oversimplifies reality. Variance measures error caused by sensitivity to the training data. High variance means the model changes too much when the data slightly changes. Good models minimize both, not just one. So, how do we know about what problem we are facing? If both training and validation performance are poor, the model is likely underfitting. If training performance is excellent, but validation performance much worse, that gap is a clear sign of overfitting. Monitoring both metrics together tells you exactly where things are going wrong. If your model is underfitting, you have several options. You can increase model complexity by adding more layers or parameters. You can engineer richer features that capture more information. You can train longer to allow patterns to fully emerge. Or you can reduce regularizations if it's overly restrictive. The goal is to give the model enough capacity to learn meaningful patterns. If your model is overfitting, the solution is usually the opposite. You can add regularizations like L1 or L2 penalties. Simplify the model architecture. Use dropout to prevent neurons from over relying on each other. Collect more training data to reduce variance or remove irrelevant features that introduce noise. Cross validation is especially powerful here. It gives a more reliable estimate of real performance. In practice, achieving balance is an iterative process. You monitor training and validation metrics continuously. You adjust complexity based on observed error, and you validate rigorously on data that truly reflects real world conditions. The best models aren't the most complex or the simplest, they are the ones that generalize reliably. Mastering the bias variance trade-off is what separates models that look good in notebooks from models that actually succeed in production. When bias and variance are both controlled, your model becomes not just accurate but trustworthy. Thanks for watching.